Hello, my name is Bill Alley with the National Groundwater Association, and my pleasure to introduce Dr. Alfonso Rivera for giving the keynote address at our meeting. Alfonso is the Chief Hydrogeologist of the Geological Survey of Canada, and he's held that position for 21 years, which is remarkable itself. Dr. Rivera is a true international hydrogeologist. And for 40 years, he's worked in Mexico, in France, in Switzerland, Germany, Spain, as well as Canada. And he's collaborated with many other researchers and universities around the world. I'm most familiar, actually, with Alfonso and his leadership of the ISARM Americas group, which was 24 countries in North and South America and Central America, too, that prepared a regional strategy for evaluation and management of transboundary aquifers. So it's the first time we looked in this hemisphere at a comprehensive look at transboundary aquifers. It was quite an effort to try to bring 24 countries, as you might imagine, together to do that. He did that very well. Dr. Alfonso holds a PhD in hydrogeology from the School of Mines in Paris and the University of Pierre and Marie Curie. Among his many publications is really a landmark one on Canada's groundwater resources, which was published in 2014. He's the author and editor of that. In addition to his duties at the Geological Survey of Canada, he's an adjunct professor at the University of Quebec and a member of the Academy of Water of France. So with that, I'll turn it over to Alfonso.
Well, thank you so much, Bill. And good morning, everyone, wherever you are located virtually. I'm very honored to be here today, and I was very honored being chosen as the keynote speaker of this year's Groundwater Summit. I very much and highly appreciate the invitation by the National Groundwater Association that allows me to be here, and this is a great opportunity to be here today. So I will deliver the keynote address today, speaking about the state of knowledge and shared management of transboundary aquifers at the global scale over the next 45 minutes or so. To do that, I have a plan to present 7 themes and a summary and conclusions on the end. So after a lengthy introduction describing the issues that I intend to describe, I will revisit the concept, the very concept of transboundary aquifers, which is still being debated somehow. You will see. I will then go and describe very briefly on the transboundary aquifers of North America and list the main outputs and most relevant outcomes of ISARM, which I will describe as well. I will spend more time, themes number 5 and 6, describing the state of knowledge and the science behind the transboundary aquifers when it comes to multiple stakes and multiple scales. And then before I summarize and conclude, I will stop a little bit and see where we are at in terms of sharing and governance and management in transboundary aquifers. So here we go. I hope you stay until the end. Really, this is a dire perspective. Let me show you the MENA region, which stands for the Middle East and North Africa region, very close to 600 million people living there. There's too much oil in the region, but too little water. It is a semi-arid and very, very arid region along this area. And there are numerous transboundary aquifers supporting water systems, socioeconomic development, and well-being of millions of people. Unfortunately, the conditions exist for water conflicts. Let's not go that far in the world. Let's stay here in North America. Let me show you now the southern border of the USA along with Mexico. Again, it's a very arid region where there are numerous transboundary aquifers supporting water system, socioeconomic development, and the well-being of more than 10 million people distributed along the boundary along 30 cities, approximately 3,145 kilometers long international border. Now, in terms of the global perspective, we have been working, as Bill said earlier, over the last 15 to 20 years, and we came out with 300 transboundary aquifers in the world, which then later, discovered more and more, 500, 590, and nowadays we have a list of 600 transboundary aquifers across the world. which are, by the way, listed in inventory in a few reports that I will show at the end of my talk. Okay, so in the very recent special issue on transboundary aquifers that I edited with my colleague Lucila Candela, let me tell you per continent. In the Americas, from Argentina, Chile, all the way to Canada, we identified 74 transboundary aquifers, 40% of which have been mapped. There is one political agreement, but many scientific arrangements. In Europe, 226 transboundary aquifers were identified. Some of them have been mapped. There's one political agreement, but many scientific arrangements. I will come back to Europe later because these transboundary aquifers are not really aquifers, physically speaking, rather water bodies to convey the management of the European Directive on the Water. Asia came out with 129 transboundary aquifers identified. Very few of them have been mapped, and there are no political agreements, signed scientific arrangements. Finally, the continent of Africa listed 72 TBAs, a few of them mapped, but there are 2 political agreements already, and many international scientific arrangements. So what I'm saying here, the main issues in a word, is that the TBA knowledge remains incomplete or is contradictory in many places. Countries do not agree on whether there is a transboundary aquifer or not. There's a very large number of stakeholders and opinions involved in the management, and large economic burden in some countries actually do not allow for full cooperation. Now, one thing that we have learned is that groundwater science alone cannot solve transboundary aquifer sustainability issues due to the complex linkages among science, management, the law, and society at large. So in general, I would say that scientists and managers lack sufficient communication. All right, let me go into the second theme of my talk today. I would like to revisit the concept of transboundary aquifers. Now, this is a three-dimensional schematic view of a multi-layer aquifer system, which is very typical of the western part of North America and Canada and the USA. By the way, I don't intend to teach you what an aquifer is. Clearly, you in this room, most of you are experts on aquifers. So that's not my intention. Rather, I would like to show the complexity when you add an additional border or boundary to aquifers. So you have rocks, groundwater, and not jurisdictions. So normally when you study an aquifer such as this one, you are interested in describing the recharge and discharge places. In this case, we are talking about a multimedia layer system where you have porous media, fractured media at the bottom here, and you have a river in connection with groundwater. So upstream, the river is recharging the aquifer. Downstream here, the aquifer is preserving the base flow of the river. So there are many pumping around, and the users are interested in see how much groundwater is there available for them and whether it's sustainable or not. So that's more or less common, you know all that. But what happens if you add a boundary? There it is again, right? A jurisdictional boundary, that is. It's fictitious, you don't see it, it's not physical, but it's there. So all of a sudden, you come up with questions that arise in addition to the ones I just mentioned, such as, whose water is it? And how much water is for me? And what about if our neighbor downstream or upstream pumps more than they should? Will my wells be dry? And what happened on my side of the aquifer? Are there international laws that will protect me? Is it sustainable? Can we manage it together? You know, there are many questions that normally you don't address. You leave them as that. In the case of transboundary aquifers, you have to address them. All right, so, but that's general. Now the UNESCO and the International Association of Hydrogeologists came up with 4 official types of TBA in the world. The first one shown here on the first slide, you have the jurisdictional border coinciding with the surface water, catchment, and groundwater demand of countries A and B. So there is little transboundary groundwater flow. In this second case, you have the surface water and groundwater device separated from the state border here. So the recharge is in one country, country A, and the discharge is in the adjacent country, country B. There you have transboundary groundwater flow. This third type shows the state border coinciding with a major river or lake where an alluvial aquifer is connected to the river. As you can see by the arrows, groundwater goes from A to the river, from B to the river. So there is little transboundary flow. This fourth official type, recognized by UNESCO, is where you have a large, deep aquifer recharged very far from the border, somewhere here in country A, not connected to local surface water and groundwater above, which have their own systems, very localized. So you are in the presence of a regional transboundary groundwater flow, that is. Now there is groundwater flow through the countries, but the scales of the time and the space are very different. So this is a problem on how to deal with them. Okay, those are the four official types. But I personally like to show that there are other types of transboundary aquifers that you don't talk very much, such as when you have lakes and aquifers and groundwater, but there is no transboundary groundwater flow through the jurisdiction. Or you have superficial aquifers and rivers where the aquifers are transboundary, but the groundwater is not. Same thing goes for when you have groundwater fluxes that may become transboundary by anthropogenic causes. And the bedrock aquifers that have fossil water or groundwater with no recharge, how do you deal with those? Or you have the same aquifer, but having different groundwater flow systems, as I will show later. And this is an issue of time and scale. And what about the multiple stakeholders' interest? That also adds additional stress into the analysis. Let me show you the Great Lakes Basin here, dividing or serving as a transboundary boundary rather between Canada and the USA. This cross section here from Lake Michigan to Lake Ontario, if you see at the bottom, the cross section, the hydraulic head distribution, at first sight, you don't see really transboundary groundwater going from one country to the other. As you can see here, most of the groundwater recharge in these parts here go to the lakes. And because the boundary, the international boundary, is in the middle of the lakes, except for Michigan, that is only the USA, then indeed you don't have transboundary groundwater, right? We should see that later. Now let me make another cross section, but only one of the lakes, Lake Huron, which is a deep lake. In this case, you have important but very localized groundwater flow indicated by these arrows here, mostly quaternary sediments, glacial sediments that feed rivers, which feed the lakes. In other words, groundwater doesn't feed the lake directly. Now you have restrained groundwater flow decreasing with depth because of confining units, and you have fossil water and whatnot. So there is little transboundary flow from the alluvial aquifer. However, the groundwater fluxes, think about it, the groundwater fluxes contribute to the water balance of the lake's basin. So should it be considered transboundary? And how about groundwater fluxes becoming transboundary with time? Now, this is another very typical case of many countries being separated by a river. You can see here, the aquifers are indeed shared by the two countries, such as quaternary deposits in yellow. But the groundwater that you see is normally being caught by the river, so it doesn't go through the international jurisdiction. Therefore, there is no transboundary groundwater. However, what happens in the same situation if one of the two countries start increasing pumping? There are more and more pumping wells, let's say country A in this case. Well, in that case, as you can see by the arrow here, dash arrow, let me put that in red. There you go. Again, there you go. As you can see now, well, the groundwater that was on country B that was used to go to the river now crosses the river underneath and goes into country A. So you have a clear case of transboundary groundwater because of anthropogenic causes. Right, let me go into my third theme today. And I thought that it was useful to show what's happening right here in North America of these three countries of this subcontinent. Canada, USA, and Mexico. And I thought that perhaps a good way to see it will be to compare the three countries and see what are the differences, what are the symmetries or asymmetries in assessment and in management and whatnot. So let me begin with Canada, where I live. So this is a very large country. This is nearly 10 million square kilometers, but only 37 million people living there. We are a very small amount of people, and the groundwater that we use in our country is 30%, about a third of the population, all users combined. Now, when it comes to managing groundwater, the groundwater resources actually are managed by the provincial governments, not by the federal government. And the recharge is estimated to be 385 cubic kilometers every year. But we only use a tiny amount of it. It's not small, but it's small compared or relative to the recharge, 1 cubic kilometers per year. It is estimated, furthermore, that groundwater in storage is in the order of 90,000 cubic kilometers. So that's more than 3 times all the surface water stored in the Great Lakes Basin. And it's also fresh. Okay, the USA, also a big country, a little bit smaller than Canada, but very big indeed. Look at the inhabitants. The population is 3 times as much, with 330. And the groundwater use is also bigger. You have 50% all users using groundwater. Now, similar to Canada, the management of groundwater resources is done by the state's government, not by federal government. Now, when you look at the groundwater recharge and groundwater in storage, you see 1,300 cubic kilometers per year and 200,000 kilometers in storage. You compare that to Canada, it is much higher. The two reasons are that climate plays a very important role. It's much colder in our country. And then the geology as well. As you probably know, in Canada, we have a very big chunk. Almost a third of the country is the Canadian shield, which is semi-impermeable or impermeable. All right, let's go and see the southern neighbor to the south of the USA, which is also part of North America. Compared to the neighbors to the north, of course, it looks like a small country, but it's not. It's also 2 million square kilometers. This is the world 14th largest. And look at the inhabitants, 127 million people. So much more than in Canada, but a little bit less than half the population of the US. However, the groundwater use in Mexico is the largest of the 3 countries, with 60%. Groundwater resources, contrary to the 2 neighbors to the north, is centralized. The management is centralized by federal government. So the states in Mexico do not manage, they do not have regulations of their own. Groundwater recharge is very similar to Canada, 307. And the groundwater use is also very, very big. It's 50 cubic kilometers per year. This is mainly due to the fact that half of the country to the north is arid and semi-arid. And groundwater in storage is 458 cubic kilometers, although it's not estimated in the same way as it is in the US and in Canada. All right, let me have a quick look to the north, boundary between the USA and Canada. So there's nearly 300 waterways along 8,800 kilometers. This is, I believe, the largest boundary between 2 countries in the world. Most of Canadians, we live in the south because it's very cold. The norther you go, the colder it is. So living watersheds crossing Canada-USA border. Now, how about aquifers? Well, we came up with this map of 10 transboundary aquifers in the world. If you can see, for example, number 6 here, which, by the way, are officially recognized by the 2 countries. The Geological Survey of Canada and the US Geological Survey work together, and these are officially recognized by UNESCO and IAH. Number 6, for instance, at the Northern Great Plains is in Manitoba and Saskatchewan provinces in Canada, and 3 states in the south, plus the 2 federal governments, or 7 jurisdictions. Okay, let me show you here the Great Lakes, because I talk about it, but you don't see any transboundary aquifer. Why? We'll see that in a minute. So this is a very special case. The Great Lakes Basin has, in fact, many unconsolidated quaternary aquifers that are contributing to the lake's balance, water balance. However, they are still not identified as transboundary, which there are currently plans to build a three-dimensional model coupled between surface water, lakes, rivers, and groundwater by the two countries, so that most likely in the near future, these aquifers will be identified with being transboundary. All right, now let's look at the south before I finish this fourth theme. The boundary, the international border along the Rio Grande, Colorado River, Mexico, and US is also large. It's 3,150 kilometers. And essentially is Colorado River to the west and about the middle center of the United States and Mexico. To the southeast is Rio Grande or Rio Bravo, as they call it in Mexico. How about transboundary aquifers? Well, there are 11 officially recognized transboundary aquifers by UNESCO and ISAR, and both countries also recognize those aquifers. But not long ago, some scientists and professors in Texas challenged that number. They say no, that there are not 11 official aquifers, there are 35 transboundary aquifers, as you can see here in this map. However, this is even though it is been published already, it is still being debated because the countries have not recognized them as today. There are many issues, essentially water security, because as I mentioned earlier, there is a very semi-arid regions here. You can see on the left-hand side, El Paso and Ciudad Juarez. This is intensive use of groundwater on both sides of the international border. And there are unsustainable water use practices. Increasing water threats and conditions for water conflicts exist. And there are international treaties, of course, but these are on surface water only. No agreements regarding groundwater resources. This point is important, and I should mention that later on when I summarize my talk. Now, there are different water management and governance approaches as well on both sides of the border. All right, so that was my third theme, and I begin my fourth now. So I hope you're still following me. I know it's difficult in virtual conversation, so to speak. So what I'll do with this fourth theme now, I will describe very briefly the main outputs and the most relevant outcomes of the last 20 years of ISAR, and I will describe ISAR itself. Perhaps many of you already know what ISAR is. This is an acronym meaning Internationally Shared Aquifer Resource Management. It was launched back in 2002 by the UNESCO International Hydrology Program and the International Association of Hydrogeologists. Basically, it means management of shared aquifers through international cooperation. That's what it is. That was the main objective. And over the years, ISAR globally involved more than 130 countries on 4 continents, 24 here in the American continent. I was very lucky representing my country, Canada, and as Bill mentioned earlier, I eventually led the group for some time. 27 countries in Europe, 38 in Asia, and look at Africa. 45 countries were involved in this initiative. So the main outputs of this global program, so to speak, is that many networks of experts were created. This is very rich. It is really rich. I have connections with people all over the world because of this transboundary program. So there are networks of experts most everywhere you can connect with. Then we also came up with a global inventory, as I mentioned earlier. So far, 600 TBAs identified. And what is interesting here, and think about it for the future, it was so important, the initiative was so important, that it attracted the attention of financial agencies, such as JEF or the World Bank, who supported activities of ISAR, just meeting together face-to-face, or mapping a few aquifers or assessing even others. And then there were novel scientific practices to define transboundary groundwater resources availability, such as the Mill River, which I will describe soon. or tools and instruments, novel tools and instruments such as GRACE, who were used to analyze very large-scale transboundary aquifers. For example, the Northern Great Plains, the Judith River, the Edwards Trinity Aquifer. And the last but not least of the opus is the United Nations drafted articles on the law of transboundary aquifers. It is the only instrument that it can be used as, at least as a guidance on how to deal with transboundary aquifers. All right, and the outcomes that are most relevant of ISARM is that some countries and some regions actually prepare regional strategies for the assessment and shared management of TVA. And alliances were created among science, policymakers, and social networks with the purpose of building trust, which is one of the main things in transboundary aquifers. Just last year, and for the third time, the United Nations General Assembly, UNGA, commended and encouraged governments to adopt the draft articles as guidance for bilateral or regional agreements for the proper management of transboundary aquifers. However, there's still perception here and there that there is no political will to establish international laws that may prove stronger than multilateral or bilateral agreements. I think this has to do with concerns of people or governments that having to see some riparian rights. And because groundwater, you can't see groundwater as you can see a river, so people are concerned about it. All right, fifth theme out of 8, don't forget. This is my favorite, state of knowledge of the aquifers, where we involve a little bit of science. I thought that perhaps the best thing to do to present this theme will be to make a direct comparison, like a checkbox, between what you call a regular aquifer and a transboundary aquifer. By regular, I mean the aquifer is located within the same jurisdiction, all right? So geological boundaries and physical boundaries, such as surface water connections, clearly are required. This knowledge is required in both the regular and the transboundary aquifer. How about jurisdictional boundaries? Well, as you can see, it doesn't check. I mean, neither the regular aquifer nor the transboundary aquifer do that. Well, it's understandable for regular, but not for the other one. Harmonized geological, conceptual, and numerical models, as well as hydrostratigraphy and the standardization of data, is something we normally do. It's a normal practice in a regular aquifer. But unfortunately, it is not in transboundary aquifers because of the discrepancies and the asymmetries of the jurisdictions. The standardization of data, the changes in boundary conditions and zoning for management is also rare even in regular aquifers and is absent in transboundary aquifers. Now, groundwater governance for shared management, shared monitoring, shared numerical models, aquifer regulations, water balances, and demands is a common practice to do this in a regular aquifer, but unfortunately not in transboundary aquifers. So this is a comparison. We can discuss each one of them separately if necessary. Let me show you just one quick example of what I'm saying here. This is the Mill River watershed compared to the Mill River aquifer. It's funny because it's the same name, but the Mill River watershed is the surface water, is the river, whereas the Mill River aquifer, same name, but it is groundwater. Now, at the time, about 10 years ago, we knew that surface water and groundwater both were located within Canada and within the USA, but also between Canada and the USA. So that made it transboundary. Surface water boundaries, the watershed, were well defined. Actually, there is a very old agreement under the International Joint Commission to deal with surface water, shared management of the two countries. But groundwater boundaries were not. You'll see here that getting closer into Alberta and Montana in the US, in the past, groundwater was considered within the river's watershed. So that would be located within this area here that I'm showing. Nowadays that we have mapped the aquifer, it has been revealed that the groundwater boundaries are superseding the river's watershed boundaries, as you can see here. Actually, it's much larger in this part of the watershed than the surface water. Therefore, the agreements do not apply as they exist. This is the hatch area that I'm referring to, that people believe that this was both the same, groundwater and surface water, and that was shared by the two countries because this is surface water. But the shared transboundary aquifer, now well defined in blue here, which is groundwater, does not have any management that is shared by both countries. Okay, before I finish this theme, I would like to say that I try to summarize what we have learned over the last 15 or so years. And there are many concepts, many ideas that are still not well understood. They are not harmonized. You know, people on one side of the border think this, and people on the other side of the border think a different thing. I'll just throw some here. For example, is it transboundary groundwater or transboundary aquifer? You might find that a little bit funny that I say this, that you will see why. How about renewable water versus fossil water? And the availability versus sustainability use? And what about space and time scales? You know, we already knew that dealing with groundwater is not the same as the rivers because the scale of the space and of time is very different. And that leads us to see what the hydraulic responses in terms of transboundary aquifers is. And how about recharge versus discharge? I don't want to complicate life anymore, but let me throw this one here. Climate variability versus climate change versus anthropogenic changes or effects. And sometimes it depends what sells better. People use the easiest, climate change. I mean, we blame it there. Or sometimes the cause is very clear. It's human change, etc. So what we're trying to do now is we are trying to clear and agree and harmonize or agree on those terms rather before we can harmonize the regional appropriateness of TBA in order to deal with shared management. It's complicated. All right, let me go into the sixth theme. Hope you're still with me. Let me check. Yes, I'm good on time. As I said, this is one of my favorites, the science behind TBA, as it deals with multiple stakes in multiple scales. I like to show this as a framework for the science of transboundary aquifer, a framework with different parts. For instance, you have a geological model, and this is a must, as I show in the table, for any aquifer, whether it's a regular or a transboundary aquifer. You need to harmonize data and agree on common hydrostratigraphy. That will lead us to the conceptual model where you add other type of research, such as hydrogeochemistry and isotopes fingerprinting when needed, which allow you to define groundwater fluxes and pools and groundwater flow systems. Having a unified databases harmonized, and that would allow you to put very, very detailed water balances. When you've done these two models, geological and conceptual, then you are ready to do a numerical model that can be used as a tool for management. This will allow you to define areas of transboundary groundwater fluxes, to validate your groundwater flow systems, to simulate the state of transboundary aquifers. It's very important. And now, in the last decade or so, we have been using remote sensing, such as GRACE, for example, or radar, or others, to constrain the models. And shared management can be done through several scenarios that you can model through this. Now, this model also helps to define time and space scale effects, which is very important in transboundary, as I show very soon. A luxury will be to have indicators for shared management. Now, that is very nice on the paper. It looks very good. But if you don't have a monitoring plan that you share with your neighbor of permanent monitoring of water levels, water quality indicators, groundwater use, and whatnot, well, you will not be able to fill in the data gaps. You won't be able to update your conceptual model, and your simulation would perhaps not be that precise. So clearly, you require a shared monitoring plan and talk the same language. Because it is a transboundary aquifer, and as mentioned already, you require communication strategies, and this is also something that we learn. Sometimes you can't move much if you don't communicate. You have to convince people. So you have to meet and engage stakeholders, sometimes even form binational teams, NGOs, etc., and integrate social science perspectives into the science framework that I'm showing here. Finally, this is the ultimate goal, if you wish. You would like to have a shared governance, which means you require social participation, you need tools, legal aspects associated to the governance, some sort of agreement, and of course, tools to manage. Right. How about multiple states and multiple scales? Well, let me show you. I mean, we're still debating. Aquifers, groundwater bodies, as they say in Europe, groundwater flow systems. Well, some scientists, including myself, are now considering parsing out groundwater flow systems rather than aquifers boundaries as a future quantitative analysis to define groundwater availability along the borderlines of TBA. Now, this is a very important outcome of ISARM because it's a matter of scale to accommodate TBA-related issues, other than just science as we know it. Let me show you two examples quickly of what I'm saying here. First, the Mill River, which is 30,000 square kilometers, and then the Rockies and the Plains, which is 10 times as big. As I showed this map before, now I will show you this aquifer here, number 9, the Mill River, shared by 4 jurisdictions, plus the 2 federal governments. Right, we defined the boundaries, as I already mentioned before, and have a look at the Medicine Hat gas field here, which is connected with the aquifer between Alberta and Montana. Now, after combining modeling with physical hydrogeology, hydrogeochemistry in isotope, we found out that most of the research is done on the south here in the state of Montana, and then it spreads out and moves radially towards the north into Alberta and southeast into Montana. Now, by combining this data, we realized that you have different groundwater flow systems with different groundwater residence time. We came out with 6 groundwater flow systems, anywhere from very recent recharged freshwater. And as you move up north, let's say about 150 kilometers or so, you have groundwater as old as 1 to 1.5 million years residence time. Same thing here in the southern part of Montana. So when you look at this, clearly it's not necessary to deal with the whole system. And you have to define what parts of the aquifer is worth sharing in terms of management. But that's not all. You also have different stakes, and the stakeholders are very important in this type of situation. For instance, municipality interests in Alberta are interested in technical and social issues, whereas First Nations in Montana here, their interests are environment and social issues. And as I mentioned, provincial government mostly is interested in allocation of groundwater and the management of the resource, at least the northern part of it. The Medicine Hat gas field, this is industry. So industry is pretty much involved because of the linkages between the gas field and the aquifer. So they are interested in gas field and well issues. Probably would not care about what's happening with the environmental and social issues of the First Nation. And the state of Montana, similar to the provincial government, are interested in groundwater allocation and management. Finally, the 2 federal governments, US and Canada, are interested in the assessment, in the planning, in the sharing, and eventually in conflict resolution. Now, the Canadian Rockies and Plains is much larger area, 300,000 square kilometers. And you may quickly say, oh, hold it. This is the same country, it's Canada. Oh, yes, it is. But we have 2 very different jurisdictions. We have British Columbia west of the Rockies, and then you have the interior plains, essentially Alberta eastern part of the Rockies. The boundary of the two provinces, it happens to be right on the watershed continental divide, which, by the way, is full of glaciers that are believed to recharge aquifers moving to the west, to the east, I'm sorry, and both east and west, but mostly to the east. Now, we studied this in different ways, including GRACE, and came up with a conceptual model that I'm showing here of the aquifer that is being recharged either by the melting of glaciers or by direct precipitation in the Rockies, infiltrate and then move to the east through a series of multiple layers that are aquifers, aquitars, etc. So we studied that. We're about to publish it now. And we came out similar to the Mill River. We came up with 4 groundwater flow systems indicated here. The associated times of residence of groundwater vary quite a lot. You have hundreds of years of water emerging in springs and lakes and rivers in the mountains, thousands of years in the foreland, hundreds of thousands of years in the foothills before going right directly into the plains, where it can be millions of years before they reach the plains. So you can see that the multiple shape and multiple scales is also a very important issue in dealing with transboundary aquifers. Okay, this is my last theme before I summarize and conclude. Shared governance and management. I have only 2 slides here, but I'd like to show you first. Keep in mind premises before I describe what we mean by shared governance and management. So as premise, we say that groundwater, I think it's clear now, is critical in water security and resilient in most of the TVA systems that we have identified so far. Now, shared management requires knowledge of TVA. Without it, you can't really manage anything. Shared governance, on the other hand, requires trust, and I put it in bold. This is extremely important. You have to trust your neighbor, but also social participation and agreed upon arrangements and a lot of collaboration. Now, management tools, legally binding or not, are required. Shared management should benefit all stakeholders, more or less equally, to follow all the principles of legal instruments. So cooperation and exchange of knowledge can help to prevent conflicts. And before I show you what I mean by shared governance, let me just quickly say that there are currently 3 legal instruments that exist and that may be applied to transboundary issues on transboundary aquifers. The UNSA Convention back in 1992, the United Nations Conventions on the Law of Non-Navigational Uses of International Watercourses 5 years after the UNSA, and the last one in 2008, the draft articles of UNGA on the law of transboundary aquifers. Actually, this third one is the only one dealing exclusively with transboundary aquifers. The other 2 has a little bit of groundwater, but not much. I would say that the core principles of the 3 legal instruments include equitable and reasonable use of the resource, as well as obligation not to cause significant harm. But there are other principles that are not necessarily legal, such as the regular exchange of data, special regard to the vital human needs, monitoring, management, prevention, control, and reduction of pollution, and protection and preservation of ecosystem. All right, now let me throw you here, similar to what I did with the science, a common framework for shared governance of TVA. This is what we came up in the ISARM Americans group of 24 countries. We require 4 components, clearly. On the one hand, we require science, which is the knowledge part of that you need to manage, but we require a strong participation of social citizens, NGOs, lawyers, industry, municipalities, whatnot. And then we will need policies as well, legal instruments. At the end, it would be ideal, although it's not always easy or possible, to have agreements that support the governance. Sometimes Sometimes you might have agreements that come directly from science, sometimes from social participation, such as the ones I'm showing here, the Abbas 4 summits between British Columbia and Washington State, the Middle River that I already mentioned, San Pedro and Santa Cruz between Arizona and Sonora in Mexico. They have no legal policies, legal agreements, but they have scientific agreements, and the knowledge is generated. Sometimes you have social and science together, such as the Ostua Metapan, a transboundary aquifer in Central America. And sometimes citizens push governments to provide legal instruments, such as in the Ocotepec Citala in Central America as well. At the end, we only came up with 3 transboundary aquifers having legally binding, policies in place, such as the Guarani aquifer in South America, shared by 4 countries: Argentina, Brazil, Uruguay, and Paraguay. The Genovese transboundary aquifer, very small, but very important. They're 40 years already managing together between Switzerland and France, and the Nubian transboundary aquifer in Northern Africa, shared by 4 countries. So there you have it. That's approximately what I wanted to tell you. And if you're still with me, I will now summarize in conclusion. All right. I hope I have convinced you that groundwater is critical in water security and resilience in most TBA systems. TBA support water system socioeconomic development and well-being of millions of people all over the world. However, the knowledge, unfortunately, remains still incomplete or is contradictory in some places. Now, we observe that a paradigm shift of scales is slowly emerging in the use of groundwater flow systems instead of aquifer traditional boundaries. We also learned that hydrology alone cannot solve TBA water problems or even resolve conflicts. We need to combine social sciences with hydrology. However, there has been a lot of progress, very solid progress in the science of TBA, like mapping and assessing. But there are delays in the policy of TBAs, in this case, management and governance. And my last slide is to tell you that there are issues to address in the coming years, particularly how do we define groundwater units of managing after everything I've said there? How do you choose the unit of management when you have an aquifer shared by 2 or more jurisdictions? We also need to design and operate frameworks for adequate governance and shared transboundary management, and increase agreements or any type of arrangements and other considerations of cooperation. Contribution on international law principles are important, and this will help sustainable management of TBA. All right. Thank you so much for your patience, and I hope you're still here. I think I'm good in time. And if you have questions, I will be very pleased to answer. I just leave my email here, and I will invite you kindly, if you are interested in this topic, you can follow us in the International Association of Hydrogeologists Transboundary Aquifer Commission, which I chair since the beginning of the year, or our LinkedIn group indicated in this way. Thank you so much.